So we're talking about divergence in particular, and a couple of rules to demonstrate divergence that they work out the exact same way as when we demonstrate convergence. So as you can see, divergence preserved under summation and constant multiplication, just as convergence does. The only exception is the difference is right here. So when you multiply something by there are more than two exceptions. For constant multiple rule, the difference is that if you multiply by 0, then you turn a divergent one into a convergent one. In the meantime, the complexity of divergence, some rule under divergence is that you don't want to do two divergent series and assume that they will diverge as well. That's exemplified here. So divergent plus divergent, we cannot say for sure that it is divergent. So it is an exact opposite of what we know about convergent. So convergent plus convergent is convergent. But we cannot say the similar. We cannot make a similar statement about divergent series. So then, as you can see, some rule for divergences in fact involves one convergent series necessarily. Okay. Okay, so the point is of these rules is similar to those rules that you see in calculus 1, where whenever it is about limits or it is about differentiation or integration, you start with simple functions, and then using these rules of algebra, you expand the scope of those operations to wider and wider. So for example, if you know that two functions are differentiable, then their sum is also differentiable, and then you know how to compute their derivative of that new function. Conversely, if you encounter a new function and you want to know what its derivative is, you decompose it into simpler functions and then apply one of the rules of differentiation in order to get there. So similarly, we are examining similar situation in terms of both convergence and divergence, but the idea is the same. Once again, expanding the scope of series that we know are convergent, as well as the scope of that we know that are divergent. Okay, so every time you encounter a new series, you might try to reduce it to a series that you have seen before. For example, if I have a series 1 over n plus minus 1, okay? So what let's say 2. Okay, so what does it converge or diverge? The answer is to try to compare it to some familiar series. It is then we don't have too many right now, but this one is what with the observation you should make here. It looks like the harmonic series. Looks like the harmonic series sum 1 over n. Okay, and then you might ask yourself, then what is it? Is there an algebra there? And the algebra is hold on a second. What is that? Well, here I'm talking about the rule that I'm trying to apply is the comparison rule for divergence. We have three theorems. Convergence theorem for divergence is comparison, summation, and scalar multiplication. So this one is you just discover that 1 over n minus 1 is larger than 1 over n. Okay, so which means that n firstly. So that's the first thing that we do in order to discover convergence or divergence of the series, is to find a familiar series that is known to which behavior is known. So the harmonic series is known to diverge. Remember, we will do it one more time later, but we know for now that it is divergent based on comparison to that integral, the improper integral. And so to begin with, then once we have that, we made that observation, then we tried thinking that maybe the series that we're looking at is in fact similar, not only in look but also in the behavior to that familiar series. So if the series is divergent, okay, divergent, then maybe the new one too. Also divergent. Okay, so that's a conjecture to be proven, and how one way to prove it is do comparison and demonstrate that a series that adds up to infinity is in fact smaller than this one. And so that's what I'm doing here. 1 over n plus 1 is in fact bigger than 1 over n. Number 1 and number 2 is sum 1 over n is infinite. So they use the comparison test or comparison rule. Then our series 1 over n minus 1 diverges. Okay, so once again, this is the rule I'm using, specifically line to this line. Okay, so a smaller series goes to infinity, then it is then the other one too. Okay, just be careful about the, as you can see, I'm using specifically here the terms, the infinities. Okay, it is not say that something series is divergent is not always sufficient. You cannot compare to some your series to a series that has no limit or has no sum. So just to say that series diverges means that its sum doesn't make sense. But there is a possibility that divergence is divergence to infinity, which does make some sense, and it may be useful for us to understand what's going on, and that's what that theorem is about. We are not speaking of series divergent in the general sense of the word. These are divergent to infinity. Divergent to infinity, which is, as I said, even though it's not as good as a number, but at least it is informative. So we know it's a pattern. Okay, so going to infinity like this. So either you do wildly up and down. That's one thing, and then there is no pattern, there is no accumulation, there is nothing long-term behavior that we can utilize. But something going to infinity, it is informative. You remember that from calculus 1. In addition to horizontal asymptotes, they are good, but there might be oblique asymptotes. There might be just function goes to infinity. It is an important thing to know about it, and then you can draw conclusions from that. And that's we are in a similar position here. The word diverges is really frequently is not sufficient for us to just to know how to proceed. It is more important to know that this series is not only just divergent, but it is actually divergent to infinity. Okay, so that's something, you know, if you have a series that is larger than a divergent series, does not mean that the series is divergent. So once again, we cannot change these infinities over here in the theorem with just the word divergent. Okay, so here's an example of a series that is, say our series is, well, negative 1 to the n. Okay, this one is divergent. And let me just put it this way, not to infinity. So in other words, it is really divergent in the bad sense, in the worst sense of the word. Okay, so n from 1 to infinity. Okay, divergent. Now if I choose another series, I could pick, for example, hold on a second, how about I start with, so this one will oscillate between, so n starting with 1, so it starts negative 1 plus 1, negative 1, so it will be either negative 1, so that's my sequences here, okay? In the meantime, if I now start adding things together, my partial sums will be negative 1, 0, negative 1, 0, okay? So that is my sequence, the limit of which I actually care to find. There's no limit, and so that's why we say it is divergent. So the limit does not exist in any sense of the word. So now if I try to compare it to, say, series that we already have seen, 1 over 2 to the n. It is a geometric series, and what is you can notice that the terms are positive. So 1 over 2 to the n will be always larger, strictly larger than negative 1 to the n, and yet so it is larger, and yet it is convergent. Okay, so then the situation is described here. Unfortunately, there is no special term to describe this when we have a divergence without divergence to infinity. So the word divergent, in fact, is, if you think about the word, it does feel like values are running in different directions. Okay, so then if you have a behavior like this, maybe it's not as much divergent as just convergent to infinity. So, but the terms typically used are these. So it's convergent or divergent at the end, and then we might be misled into thinking that there is nothing for us there for us to discuss. But this is a bad case of when it is indeed true. There is nothing to gain from studying the series because it has no meaning. But this one that's the different one. This one, the harmonic series, in fact, diverges to infinity. Okay, so there you go. So this we also discovered that, in fact, in the previous example, that 1 over n minus 1 diverges to infinity. Okay, so once again, it is informative. Okay, so there is one most important, in fact, test for divergence. It is and it is the simplest one too. So it's called the test for divergence. And well, the one that we just looked at, n is equal to -1 to the n, the sequence of plus or minus 1, and when it is adapt to -1, 0, -1, 0, partial sums. Okay. So it is certainly diverges, and the series diverges because there is no limit. That's the meaning of divergence of a series, is there is no limit of the sequence of partial sums. But that's hard to find out. As you have seen already, adding things together is complicated. So is it possible to ever, under any circumstances, to predict that the series will diverge by looking at the sequence itself? So something that we do not do, because as I said, this is the definition, and this is what we really look at every time we study a series. We look at partial sums. Okay, but is it possible not to try to look at the partial sums, so try to figure out what they are? Is it possible to tell that it diverges? And it is possible sometimes, and this is it. What if the pattern of the sequence of the original sequence, not the partial sum, but the sequence itself, is that it actually diverges. Okay, so you take a divergent sequence and start adding terms, then that is the claim that I'm making, is that it's not going to be it's not going to adapt to anything that is divergent. Okay, so if the series sequence itself, the original sequence, is divergent, then so will the sequence of partial sums. This is the illustration. The illustration when of that idea that, to begin with, that a divergent sequence will not produce a convergent sequence of partial sums. Okay, a divergent sequence won't produce a convergent sequence of partial sums. So that's the first observation that we make. At least that's what this example suggests. We start with a divergent sequence. When we start adding it together, there is no way for a pattern to emerge, and indeed it doesn't. Is it the only case when we can once again, the idea is to examine the sequence, itself, and try to draw any conclusions about the series. And one of the observations is the sequence might be divergent itself. However, it is not necessarily is not necessary. So this is sufficient to ensure divergence. Okay, but not necessary. Okay, yes. So there, in other words, there might be a sequence. We know, in fact, examples of sequences that are convergent, but the series still divergent. It's very simple, in fact. How about I just pick one? So a constant sequence of ones. So my sequence will be 1, 1, 1, 1. It is convergent. It converges, and yet we know that if we start adding up these terms, and partial sums will be 1, 2, 3, 4, and it diverges. Okay, so this one diverges nonetheless. Okay, so of its own, it doesn't necessarily mean divergence. As you can see, it just goes to infinity. So then what is the observation that we can make from this example? We have divergence, and what is so wrong with the sequence? I mean, that's if you remember studying sequences a month ago or so, then this simple sequence that we start with. An is constant sequence, so it's not only it converges in a best way possible. It's just does not change. Okay, and yet when we start adding terms together, we have divergence. So what is wrong with such a sequence? Well, let me give you, before we actually make an observation, we can have another example which hopefully will help. I take another constant sequence, but what is if it's made of zeros? So then I have 0. The sequence converges, and the partial sums are also all zeros, and once again it also converges. So in fact, if you think about it, picking any constant sequence will give you a divergent series unless that number is 0, right? That's it. So no matter how small a number is, you start growing, it will go to infinity. So then what is the difference? The difference is between 0 and non-zero, and so that's the observation. That is actually our interest is. So we have to concentrate on a sequence that is already convergent. That's the first observation. So suppose we have a convergent sequence, a sequence convergent to any number other than 0. Won't produce a convergence sequence of partial sums. Okay, so not only constant sequence made of numbers other than 0 won't converge, partial sums won't converge, but any sequence, if you start adding numbers that are not getting smaller and smaller, okay? So sequence, you have a sequence, and when you start adding those terms together, little by little, one by one, then if you add terms every time, and that these terms are not diminishing, then there won't be any accumulation of values of that sequence. Okay, so as an example, it doesn't have to be a constant sequence, but here's one. If I take an is equal to, say, 1 plus 1 over 2 to the n. Okay, so a sequence that certainly is convergent, it converges to 1. Okay, so and then I start doing partial sums, and I'm adding numbers that are well behaved, but they will be simply, every time there will be 1 present there. So 1, what is it? 1. The first term is actually the first term is 2, and well, let me put it this way. So it will be 1 plus 1 over 2, and then I add 1 plus 1 over 4, and then I add 1 plus 1 over 8, and so on. So as you can see, even though the sequence that I have in parentheses, the original sequence is convergent, it converges to 1, you can see that every time we have a 1 present. And so if you start adding those things together, there's no way for this thing to end up anywhere but infinity. So that gives me divergence again, and that is called the test for divergence, the last one. So this is the theorem. If an does not converge to 0 as n goes to infinity, then some an diverges. Let me state it in the contrapositive way. If the sequence does converge, if the series does converge, then the sequence has to converge to 0. Okay, so that quickly takes care of that previous example when you cannot possibly there's no convergence to 0 of the elements of the sequence, and so there is no convergence of the series. Okay, so that's the contrapositive. You can see it's the same statement. So the theorem, and then I state it in the contrapositive form. So either you go from this sequence to series, or you turn these things around and you go from the series to sequence. As you can see, what has happened is I take the negative of each of the two statements and reverse the order of the implication. So the contrapositive, you've seen contrapositives before, right? So that's a good example of how you can turn it around, and you pretty much, depending on the circumstances, you might need one or the other, and so you have to switch back and forth as needed. And as you can see what has happened is, once again, the order has changed, sequences to series, from series to sequences, and each of these statements have been negated. So divergence becomes convergence, and convergence becomes divergence. Okay, so we'll use this in the future, but first I want to state the converse. What's the difference between the converse and the contrapositive? Frequently you say conversely, so you make a statement and then you say conversely, this is true. So let's take the theorem. So if an does not converge to 0, then the series diverges. What's the contrapositive of what is the converse of that? When this an goes to 0, then some converges. Some an converges. If yes, this is the converse. And once again, you can take the converse of the contrapositive, and that would be another version of the converse. Okay, so the only thing we need to look at now is is the statement true? So the theorem, this remains to be proven. We're going to do that in a minute. But what about the converse, which is not the same statement? These two are the same. So this is the same statement. It's just two forms of the same statement. Okay, but the converse is a different statement. Okay. So is it true?
No.
This is false because, how do we know?
Of the constant multiple, like say a to n, or a of n equals -1 to the n.
Yeah.
That would be an example.
-1 to the n. Yeah, but it does not go to 0. It is indeed false, and you need an example where these two conditions are satisfied, both of them. So the sequence has to, no, not both of them are satisfied. The first condition is satisfied, but the second is not. So you need, as an example, or it is called a counterexample. A counterexample to a theorem is to show that there might be a n going to 0, but the series diverges. We had that. What's the series? The harmonic series. The harmonic series is the example of this when even though the sequence itself converges to 0, and yet when you add up together, it does not guarantee anything about the series. So you add small and smaller numbers, small and small, and they go to 0 pretty quickly. However, they are not quickly enough, and they are add up to infinity at the end. Okay, so we showed it with once again with that comparison to integral 1 over x, the integral of 1 over x, which is logarithm, and logarithm goes to infinity. Okay, so a counterexample demonstrates that this is false, and so we don't have to worry about it. So let me cross it out just in case. The statement itself is simply incorrect. It goes only one way. It is a significant simplification. Well, we shouldn't expect simplifications of this nature. So the transition from sequences to series is hard, and even sometimes we might know a lot about the sequence itself, and it might or might not tell us anything about the series. And in the negative sense, it does. That's the theorem. The direct statement of the theorem is it is informative. That we can discover divergent series, but we cannot reverse it, and the convergence is not guaranteed no matter what we know about the sequence or the original sequence, or at least for now we don't have any anything of that kind, unless it's something specific like a geometric series. So, for example, if you know that an is a multiple, you multiply by the same number you want where the ratio is less than 1, between -1 and 1, then you have convergence. Otherwise, we have no general idea of what's going to happen. So anyway, let's prove it. It's not that bad, but it does require proof. So we have sequence an, and we know that what do we know? We're going to go. I'm going to go with the counterpositive. So I have a convergence. This one. Convergence series, and I want to demonstrate that the sequence where it came from is convergent to 0. Okay, so so sum an is convergent. Now we have to take this apart in order to examine. So that the means, what this means is that the sequence of partial sums is convergent. So Pn converges to some P, whatever that number is. So we know, and now we go back and once again we're unwrapping everything, and I'm gonna so I have to actually point out the direct relation between the two. Right? That's what the theorem is about, the relation between the partial sums and the sequence itself. So Pn, and we have a recursive formula, Pn plus 1 is equal to Pn plus An. That is the relation. We are adding up the elements of An. Okay, so so that's the definition of the partial sum. Now I just flip, and I have An is equal to Pn plus 1 minus Pn. Okay? And now let's examine what we've got here. Let's examine the right-hand side. So what do we know about the limit of the right-hand side? What do we know about the limit of the right-hand side?
It should be equal to the limit of the left-hand side.
Well, yeah, but I want to discover something about the limit of the left-hand side by understanding what's happening with the limit on the right-hand side. So I have to look at it independently. So what do we know about the participants on the right? Nothing but this. This is the only thing that we know. Okay, so what do we say about the then? Well, Pn goes to P. That's what we know. What else do we know? Where does Pn plus 1 go? Pn plus 1 is, what's the difference between Pn and Pn plus 1? So question here. Pn is, as a sequence, it is P1, P2, P3, P4, right? Whatever they are. If I now try to list Pn plus 1, what do I have? So this is the first one, the second, the third, the fourth. Okay, what is the first element of the second sequence? P2, that's right. N is equal to 1, then the element will be equal to P2. Okay, so if you like P2, P3, P4, P5, on and on, that's my new sequence. Okay, so what kind of sequence is that? What's the, it's not the same sequence as the last one, but what can we say about the second sequence?
It would be equal to P plus A n.
No, you're still going backwards. You're going back to AN. We cannot discuss AN. We try to draw conclusions about AN. So we have to concentrate on this part of our equation, figure out what this, how it behaves, and then that will translate that into our information about AN. Okay? So once again, what is the relation between these two sequences at the bottom? They look very similar. Well, think about the graph. What's the difference between the two graphs? Shifted left. It shifted to the left. Yes, but yeah, the point is it is shifted. It is nothing but a shift of the original one. So let me. So 1, 2, 3, 4. Okay. So if I have my P, say this is P1, this is P2, this is P3, this is P4. Now if I'm trying to plot the other one, I'm going to have P2, and the first location, this will be P2. That's my second sequence. P2, P3, P4, and here somewhere will be P5. So this is like Qn. If this is my sequence Qn, if I give it a new name, So just for convenience, I have a new sequence, and it is defined according to Qn is equal to Pn plus 1. Okay, so a new sequence that I have defined, it is very similar to the original one, except as you can see, what we observe here is it is a shift of the original one like this. So the whole graph, I'm zoomed in right now, but you can imagine that if I zoom out, these two graphs they will look like graphs of functions, so they will have exactly the same shape. It's just shifted. Okay, so what does it tell us about the new function or new graph or new sequence? Well, what is that we care about it? Remember, these are sequences, so as far as sequences are concerned, the only one we think that we really care about. What is it? The limit. Right? So it doesn't really matter how the sequence B is, as if we know its limit, that's pretty much all we care about. Okay, so what about the limit of Qn? So let's zoom out. If I zoom out, then I have so this is my Pn. Zoom out, so those points will be so close to each other that, well, I don't want to assume that anything specific about it. This is my Pn, okay? And we know that, what do we know about it? We know this. We know that there is a convergence to P. So in other words, there is like an asymptote, and this is y equal P. Okay, now if I take the other one, Q, and it is shifted, how do I plot Qn? The one in purple. What does it look like? No, look at those blue air. Well, you said it. You thought it was to the right, but it is to the left, but it's still a horizontal shift. No, it's not a vertical shift. It's a horizontal shift. Below, yes. If it is, if the graph is the one the way I plot it, it will be indeed just under it to the right. It is in fact probably describing it as under it is a little bit unfair, because if the shift is horizontal, let's just say it is horizontal, it will look like this. It will look like this. So I'm shifting it like this. It is definitely under it the way it looks, but the shift is not vertical. Okay, if you shift it vertically, by the way, it will dip below the line P. And this one is not dipping below line P because the shift is horizontal. So everything remains above line P. Okay, so the big conclusion that we make about Qn is what? That's right. The limit of P of Qn is still is equal to P, right? So if it was that infinite tail will be. I mean, if you zoom out even more than this, then what's happening to the graph of P, same as to the graph of Q, they will be merging, virtually merging with the horizontal line y equal P, and without distinction. It's sort of, in a way, Qn arrives. It arrives to the same to the same place, only one step, which is only one step behind, right? So the conclusion that Qn is equal to P, that might require, if you really care to examine it, it might require a little bit of a proof with referring to the definition of the limit, but it is certainly, the picture itself is very revealing. The shape of the graph is the same, and then you can invoke any kind of ideas that you on the subject of horizontal asymptotes from calculus 1. So once again, shifting a graph horizontally will not change its horizontal asymptote. You're just sliding along that asymptote, right? So this one is even simpler because these are sequences. Okay, so the limit is the same, so then we are then with all this analysis now finished. We take it back and we take it back here. Okay, so turns out that our sequence, let me start writing over, so an is equal to pn plus 1 minus pn, or as we have renamed things, it is qn minus pn, and now we're just going back and they have the same limit. As n goes to infinity, they have the same limit, and so the conclusion is that the limit of a is what? Well, let's carry out this computation with explicitly. So I have a limit an is equal to limit qn minus pn. Okay. At this point, I want to express the I want to split the left hand side. So I'm sorry, the right hand side. So how do I split it? So we are speaking here entirely of sequences, not of series, but still, so what do we know about limits? The limit of a difference of two sequences is equal to what? Difference of the limits. Right, so in other words, it is a sum rule of limits, limit qn minus limit of pn, and it is it has to be justified, this transition. Unfortunately, all the caveats, the warnings are there because it is justifiable because both series converge. I'm sorry, not series, sequences. Both sequences converge. So that's why it works out. That's why the sum rule is applicable. We just demonstrated right here, qn converges, pn converges, so both of them converges, so we split the limit into two, and then we know that each of them is equal to p, and so altogether the whole thing is equal to 0, and that ends the proof. So limit of an is indeed 0. In fact, if you think about it, if you look at that last picture right in the middle, where is an? Well, start with on the right. The picture on the right. Where is an? It is pn plus 1 minus pn, or qn minus pn. So this is it. Over here, this is a1, this is a2. It does not contribute anything to our proof, but if you want to see the proof in one picture, then you, or two pictures, you look at the picture on the right to point out where AA's are. They are simply the difference between P's. Okay, and then now if you finally take a look at the picture, it's very hard to fit, but these are the A's. Well, the distance, the A is the distance between the two graphs, and you can see it disappearing. Okay, so that is one picture explanation of the proof rather than algebraic proof that we have here. Okay, so two, once again, so think about take a graph with an asymptote, shift it to the left, and then compare the two graphs vertically. What's going to happen is that those distances between them have to diminish. Why do they diminish? Because they have the same horizontal asymptote. Okay. Divergence test. Okay, so let me just start on the next one. So this divergence test is whenever you encounter a series, the number one thing to verify is that test. Look at the sequence itself, where it comes from, and make sure that it goes to 0. If it does not, you're done. There is nothing for you to do because the series diverges. The end. Okay. So this is there. There is sometimes more. There are more shortcuts. If the series have non-negative terms. So AN starts this way. This is the starting point. Then you have a sequence, and then each term is non-negative. Okay? Then if you think about it, then Pn plus 1, as we just discussed, is equal to Pn plus AN. So you start with you start with 0, and then you start adding things, and these things are non-negative. So what kind of sequence is Pn? You add more and more, so
It'd be divergent.
no, not necessarily. It will be increasing. Increasing sequence, yes, because we are adding a positive number every time. So this will be Pn plus 1 is Pn plus An, which is larger than or equal to Pn. So Pn plus 1 is larger than Pn. It is just an increasing behavior of function that we see. So the series will look like this. These partial sums might grow. They might grow to infinity like this, or they still might stop and level out. So the good news is that this is not going to happen anymore. So this one is out. That's unpleasant. Possibility of going up and down is not going to be our concern anymore. There are only two outcomes: either convergence here or divergence to infinity. These are the only two. Okay, so that makes life easier. Okay, so I'll see you next week.